In section 5.8, we're continuing our substitution topic, and we'll have a lot more problems dealing with substitution, but primarily the main thing that distinguishes section 5.8 from 5.7 before it is it's the addition of the inverse trig functions in it. So I do need you to recall from Calc 1, when we took the derivative of the inverse sine of x, we got 1 over the square root of 1 minus x squared. Now, we need to remember in this class that anytime we integrate 1 over the square root of 1 minus x squared, we're going to go backwards and get the inverse sine of x plus the constant of integration. Now again, remember that dx could be in the numerator or out to the side. Either way, I need to understand it means the integral of 1 over the square root of 1 minus x squared with respect to x, which has this integral. Well, we also know that the derivative with respect to x of the inverse tangent function is equal to 1 over x squared plus 1. Well, now when I integrate that, the integral of 1 over x squared plus 1 with respect to x is equal to the inverse tangent of x plus the constant of integration. Finally, and this one won't be used nearly as often, but if we took the derivative of the inverse secant of x in Calc 1, we need to remember that has the derivative of 1 over the absolute value of x on the square root of x squared minus 1. And then now the counter integral to that is, well, if I'm integrating 1 over the absolute value of x on the square root of x squared minus 1, I need to understand that that's the inverse secant function plus c. Now remember, we had these three derivatives. If I wanted to take the derivative of the inverse cosine, it's just negative 1 over this square root of 1 minus x squared. If I wanted to take the derivative of the inverse cotangent, it's just negative 1 over x squared plus 1. And similarly, if I wanted to take the derivative of the inverse cosecant, it's just negative 1 over this absolute value of x on the square root of x squared minus 1. So whenever we have a negative in here, we can just call it the negative of the inverse sine, or we could call it the inverse cosine of x, either way. Now, keep in mind, that's not saying that the negative of the inverse sine of x is equal to the inverse cosine of x. It's just saying that the shape of the functions are the same. The only thing that differs, the only thing that's different between them is some constant value c. Now, let's go ahead and break into this section. Oh, and you'll see I didn't mention the last one because we should already be familiar with it. Derivative of any exponential function is that exponential function times the natural log of its base. So when I integrate an exponential function, I'll say, well, the integral is that exponential function divided by the natural log of its base plus the constant of integration. Now, let's look at a problem. Now, this problem is going to involve a natural log in my answer. And the reason I can see that is almost every time the degree of your numerator and denominator differs by 1, it's going to be a natural log because the derivative of that polynomial denominator is going to be a constant. You have a constant in the numerator. This is going to simplify down to be 1 over u du, which is going to be the natural log of the absolute value of u. But let's see how we get to that with the substitution. In this problem, first thing, as soon as you look at it, you should say, well, I'm going to let u equal that denominator, 3t plus 4. If I do that, the derivative of 3t plus 4 is just going to be 3 with respect to t. So then I can say, all right, well, if u is equal to 3t plus 4, then u evaluated at 2, it's going to be 3 times 2 plus 4, it's 10. U evaluated at 4, 3 times 4 plus 4, I get a 16. And so now the original integral in this step, I'm just showing that the integration is possible. We had to show in order for the integration to be possible that I had a factor of 3 dt in there. We didn't initially, but you could easily multiply the inside by 3 if you divide by 3 on the outside. So that's what I've done here. And then you can say, well, all right, now let's change the limits of integration and put everything in terms of u. From this step to this step, I keep the 1/3 out in front. And again, remember that 1/3 was necessary to get the factor of 3 on the inside. The 3 dt becomes du. So then you're left with 1 over u du integrated from the lower to upper limit of 10 to 16. So now I can say, well, the integral of 1 over u is just the natural log of the absolute value of u. I don't really need the absolute value in this case since the values of u are positive anyway. But now to simplify, you can say, well, this is going to be 1/3 the natural log of 16 minus the natural log of 10, which is where this came from. And then you wouldn't really have to simplify that down, but I was just showing here when you condense, anytime you subtract separate logarithms, you could divide their terms. So that would be the natural log of 16 divided by 10, which is the natural log of 1.6. And then you could call it 1/3 the natural log of 1.6. I chose to put that 1/3 up as an exponent, and instead of saying the 1/3 power, I put the cube root of 1.6. So it's the natural log of the cube root of 1.6. Any of those answers would have been fine, though. In fact, the preceding answer where I didn't simplify would also have been fine. Let's look at a second one here. Again, I'm giving you a definite integral. This one's really quick, though, because you can just see it's automatically in the form the integral of 1 over the square root of 1 minus x squared. As soon as you see that, you don't have to do a thing. It's just the inverse sine function by definition. So I'm integrating the inverse sine from -1/2 to the square root of 3 over 2. That's going to give me the inverse sine at the square root of 3 over 2. It's asking you, when is your sine function the square root of 3 over 2 between -pi/2 and pi/2? And you can say, well, that's going to occur at pi/3. At pi/3 radians in quadrant 1, your y value on the unit circle is the square root of 3 over 2. Now, minus the inverse sine of -1/2, that's asking you, when is your sine function -1/2? You can say, well, the sine function is -1/2 down in quadrant 4 at an angle of -pi/6. So I get pi/3 minus a -pi/6. That's going to be 2pi/6 plus 1pi/6 is 3pi/6, which simplifies to pi/2. That's what we do. This next one, in order to simplify it here, I have the integral of dx over 4 plus x squared. So what I'm doing here is I'm trying to force this to be in the format of one of these problems up here. I can see anytime I have a term in the denominator squared plus a constant, it's probably in the inverse tangent format. But the inverse tangent format is 1 plus x squared. Well, this is 4 plus x squared. Well, okay. First thing I'll do is I'll factor out a 4. But when I factor out a 4, yes, that's going to give me a 1 for the first term in that denominator, but it also gives me a 1/4 as the coefficient of x squared. And so now the problem is, well, I need a 1 plus a variable squared, not 1 plus 1/4 a variable squared. That instantly sets up our substitution. I'm going to let u squared equal 1/4 x squared, but I can't do that unless I account for du. So if u squared is that, take the square root of both sides, u is going to be 1/2 x. Well, then the derivative of u is going to be 1/2 dx. So in order to do this substitution, I have to see a 1/2 dx inside of the problem. Well, okay. If I multiplied the inside by 1/2, I'd have to multiply the outside by 2. That's where this 1/2 came from in the next step. 1/4 times 2 is 1/2. Now the 1/2 dx becomes the du in this step. My denominator, 1 plus u squared, since u squared is 1/4 x squared. Now, the inside is defined to be the inverse tangent of u. So I'm going to have 1/2, the inverse tangent of u, of course, plus the constant of integration. And then we can say, well, substitute back in u. We know u is equal to 1/2 x inside of an angle. It's probably better to write that as x over 2. That's what I did here. 1/2 inverse tangent of x over 2 plus your constant of integration. Now, another definite integral. So the first one I did just involved a natural log. Then we went to an inverse sine, inverse tangent. Let's look at this next one. So I have Please notice in this problem, it's automatically in the format of the inverse secant. You can say, well, okay, 1 over the absolute value of x on the square root of x squared minus 1. If that's inside of an integral, I need to understand that that's going to give me the inverse secant of x plus the constant of integration. Now, inside of a definite integral, I will not have the constant of integration, but please do notice you have 1 over, and I don't need the absolute value of x, and think about why you don't need it. You already know that the only x values in this problem are from a positive 4 over the root of 3 to a positive 4 over the root of 2. That's automatically positive anyway. So the absolute value doesn't need to be there, so I can think of that as 1 over the absolute value of x on the square root of x squared minus 4. And I can say, well, that's similar to my inverse secant format, except it needs a 1 inside of that square root. So I need to factor out the square root of 4 in the denominator. I know that the square root of 4 is a 2. That's going to factor out as a 2 in the denominator on the outside. Now I go back to the inside. My numerator is still dx. I still have that x. But inside of this group, I factored out the square root of 4, which again came out as a 2. That's going to make this first term 1/4 x squared minus 1. Now I can say, well, it's still not quite in the format that I need, because that's supposed to be a variable squared instead of 1/4 times a variable squared. So just like last time, I'm going to let u squared equal 1/4 x squared. And so u is equal to 1/2 x. Derivative of u, 1/2 dx. Now, when I come down and try to make sure that this can work out, I can say, well, then in order for this to work, I would need to see a 1/2 dx in there. Well, I would multiply the inside by 1/2, which means I multiply the outside by 2. That 2 and the 1/2 cancel. That's why you'll see I did not put the 1/2 down here in front of the next step. Canceled out with me having to put this 1/2 there, having to multiply the outside by 2. So now my numerator is du. My denominator, I had an x there. Well, that x I need to understand is equivalent to 2u. If u is equal to 1/2 x, then 1x is equal to 2u. So I replaced x with 2u, and now inside this square root, 1/4 x squared can be written as u squared minus 1. Now it looks like I just forgot to put the 1/2 in this step. I did not. Please understand why that 1/2 disappeared. It disappeared because of trying to force the factor of 1/2 to the inside, multiplying the outside by 2. But now that 2 that I got from the substitution of the x is equal to 2u comes back out in front, and I have a 1/2 out in front again. But at this point, I also need to change my limits of integration. So I'll say, well, my original limits were in terms of x. My new limits need to be in terms of u. I know u is just equal to 1/2 of x. So you can see all I did is I took each of my x limits and divided them by 2. So 4 over the root of 3 becomes 2 over the root of 3. 4 over the root of 2 becomes 2 over the root of 2. So these are now my limits with respect to u. This is now just going to be the inverse secant of u times 1/2. I'll divide by 2. And I have the inverse secant of u divided by 2 evaluated from the lower limit to the upper limit. Now, the inverse secant of 2 over the root of 2, that's saying that's the same thing as the inverse cosine of the reciprocal of that argument, square root of 2 over 2. And then the same thing for the denominator, it's going to be the inverse cosine of the square root of 3 over 2. Inverse cosine of the square root of 2 over 2, that's going to be pi over 4. Pi over 4 divided by 2 is pi over 8. Inverse cosine of the square root of 3 over 2, it's asking you when is your cosine the square root of 3 over 2, and that's going to be at pi over 6. Pi over 6 divided by 2, pi over 12. For the final answer here, we get pi over 8 minus pi over 12, which is the same thing as 3 pi over 24 minus 2 pi over 24, or 1 pi over 24. Now, you're thinking, that's a pretty good problem. It is. Not a whole lot of substitution had to go on in it, though. So if I look at another one here with these transcendentals, let's say I have an inverse cosine inside of a natural log within a problem. As soon as I see I have that inverse cosine in the denominator, I know the wise choice for my u substitution is going to be, let's let u equal that entire inverse cosine of x, because then the derivative is going to be 1 over the inverse cosine of x times the derivative of the inverse cosine of x. So that's what I've done here. If this were my original problem, then I can say, all right, I'm going to let u equal the natural log of the inverse cosine of x. Now, the derivative of that natural log, derivative of every single natural log in existence, 1 over what's inside the natural log times the derivative of what's inside the natural log, and this derivative is with respect to x. So now I look at my problem and say, well, all right, I have the 1 over inverse cosine. I have the square root of 1 minus x squared in the denominator. I don't have a factor of -1 in the numerator. So I would just know I need to multiply the inside by a negative in order to replace that, all of that with a du, which means I need to multiply the outside by a negative. Now, all of this cancels out all of that on the inside, and the only thing you're left with is that natural log of the inverse cosine of x. Well, I know that that's u. So I get the negative of the integral of u with respect to u. Power rule tells me that that's going to be u to the second over 2 plus your constant of integration. And then I can say, all right, I have the negative in front of that group. I'll distribute the negative into just the first term, because you never really put a minus c. It's always plus the constant of integration. I'll get -1/2 times the group of the natural log of the inverse cosine of x quantity squared. And you have to make sure that that square is on the entire natural log and not just on the argument, the inverse cosine of x. All right, that's a pretty cool problem. My next one, pretty quick. What if you have an algebraic times an exponential function? You say, okay, anytime that exponent is not a linear function, you know you're going to have to use substitution for that exponent. So if I let u equal x squared here, then du is going to be 2x with respect to x. Now, I only have an x dx, so I would need to multiply the inside by 2 in order for this 2x dx to become du. But if I multiply the inside by 2, then I have to divide by 2 on the outside. This becomes 1/2 the integral, and I'll have 10 to the u, and all of that is du. But then I can see that my answer is going to be 0 as soon as I change my limits of integration. You can say, well, your lower limit of -2, if you plug that into u of -2, -2 squared is 4. Same thing as 2 squared, also 4. So your lower and upper limit, it's going from 4 to 4. So I went ahead and integrated just for the sake of the integration, though I knew that the answer was going to be 0 since I'm starting and stopping at the same number. But the integral of 10 to the u would be 10 to the u divided by the natural log of 10. Of course, I keep my 1/2 out in front. But then, as soon as I evaluate from 4 to 4, we know anytime you start and stop at the same point, you're not giving the integral any time to collect area, so our answer has to be 0. Now, for this next one, I have an exponential function inside of a square root function. I have the integral of dx over the square root of 5 to the 2x minus 1. Now, what I wanted to make sure you understood in the first step, oftentimes we let whatever's inside of a group to a power be what our u substitution is. And so you might think, well, hey, I'll let 5 to the 2x minus 1 equal u. That'd be a terrible idea. And the reason that that would be a terrible idea is because du would have to have 5 to the 2x times 2 ln 5 dx. I don't have a 5 to the 2x as a factor in the numerator, and you can't multiply by any function in terms of x on the inside. The only thing we can ever multiply is a constant on the inside and then divide by that constant on the outside. Can't multiply by 5 to the 2x, so I cannot let u equal that term inside the group inside the square root in the denominator. So now what I'm going to do instead is I'll say let's look at that square root in the denominator and work with it algebraically. I'm going to factor out a 5 to the 2x power in there. If you factor a 5 to the 2x out of itself, you just get a 1. And if you factor a 5 to the 2x out of 1, you can say, well, that's 1 divided by 5 to the 2x, which could be written as 5 to the negative 2x power. That's all I've done in this step right here. Now I can simplify this and say, well, I know that the square root of this 5 to the 2x, remember the square root is acting like a power to a power, so you have 5 to the 2x raised to the 1/2 power. 2x times 1/2, that's just 5 to the x power. Now, times the square root of 1 minus 5 to the negative 2x. Now, what I'm saying in this format is to please notice I have the square root of 1 minus u squared. This is 1 minus 5 to the negative x quantity squared inside of there. So I can say, well, all right, if I'm going to let u squared equal that 5 to the negative 2x, then u is the square root of that, which is 5 to the negative x. The derivative of u, well, derivative of any exponential function is that exponential function times the derivative of its exponent times the natural log of its base with respect to x in this case. Now, I already see I have the 5 to the negative x in there as a factor. It's right there. 5 to the x in the denominator is 5 to the negative x power. I don't have the negative 1 in the natural log of 5, though. So I can say, well, all right, I'll need to multiply by a negative 1 and a natural log of 5. If I do that, I need to divide by a negative 1 natural log of 5 on the outside. So that's where that negative 1 over ln 5 came from on the outside to take care of the fact that I had to multiply it on the inside. Now, from this step to the next, all of this is going to become du. My square root, that's going to become the square root of 1 minus u squared. So I'll have 1 over the square root of 1 minus u squared. Everything else just became du. I still have my coefficient factor out in front, negative 1 over the natural log of 5. But now as soon as I see, oh, 1 over the square root of 1 minus u squared, by definition, that's the inverse sine of u when we integrate. So I get that. And then plugging in what we know u is 5 to the negative x. I could have put that this is negative 1 over natural log of 5, inverse sine of 5 to the negative x. I chose to write that as 1 over 5 to the x in for the angle and the inverse sine function. No big deal there. Plus the constant of integration. So I'll say final answer like that. And again, if you wanted to put 5 to the negative x as that argument, it'd be no problem. For the next one here, soon as I see I have a degree difference, if my numerator is a polynomial and my denominator is a polynomial, anytime I have a degree difference of 1, I'm automatically thinking, this is going to be a natural log. Well, let's see that in this problem. If I let u equal the denominator, u is equal to x squared plus 1, well, the derivative of that, I get 2x with respect to x. So then I can say, well, but my numerator is a 4x, not a 2x. Well, you can factor a 2 out of that, and then your 2x dx is all going to become du. And so then you've got, well, that's going to simplify to 1 over u du, which we know is the natural log of the absolute value of u. So I get 2 natural log of the absolute value of u plus the constant of integration. Now I know u is equal to x squared plus 1. So that absolute value can actually go away because x squared plus 1 is automatically positive anyway. So we'll get 2 times the natural log of x squared plus 1 plus our constant of integration there. That's a good problem. But something I do want you to keep in mind is when you have a rational function in there, polynomial numerator and denominator, if the degree difference is 1, your answer is going to involve a natural log because the derivative of the denominator can be in the numerator. And anytime that's the case, it's going to be the natural log. Just like here, derivative of u with respect to u is 1. Oh, then that's the natural log of u. Absolutely. In this next one, gorgeous problem. We have the integral of dx over the square root of 9 minus 16x squared. Okay, So in this one, I'm hoping that you recognize it's in the format of the inverse sine of x. 1 over the square root of 1 minus x squared is equal to the inverse sine of x plus c. Well, we have a 9 out in front of this one that we have to get rid of. So that's the first step I did. I factored out a square root of 9 in that denominator. That came out as a denominator of 3 on the outside, since the square root of 9 is 3. And then that leaves me the square root of 1. Then I had to divide 9 into this term, minus 16/9 x squared. That automatically sets up my substitution. I'm going to let u squared equal 16 over 9x squared. Take the square root. U is going to equal 4/3 x. And then we can say, well, then the derivative of u is going to be 4/3 dx. Now, in order to do this substitution, I would have to say, well, in order to have this, I'd have to see a 4/3 dx. I don't see a 4/3 dx in there. If I could put a 4/3 dx, I can replace it with du. That's what I've done in the next step. But in order to do this du in the next step, I had to have a 4/3 there. So I'd need to multiply the inside by 4 over 3, which means you need to multiply the outside by 3 over 4. That's where that came from. So my outside is going to be 1 over 3 times 3 over 4. The 4/3 dx is replaced with the du. And then my denominator is just the square root of 1 minus u squared. By definition, that's the inverse sine of u. I'll have 3 over 12, which reduces to 1/4 inverse sine of u, plus c, which is just 1/4 inverse sine. And I know that the u value was 4x over 3. I would prefer to write it like that instead of 4/3 x. It just looks better inside the inverse sine function, plus our constant of integration. One more page for this section. Let's say we're looking at a problem where everything in there is an exponential. There's an easy way to work this problem and a hard way. The easy way is just to understand that you can algebraically simplify first. You don't need any substitution or anything else. You just go ahead and say, well, if I have 2 terms divided by 1 term, then I can distribute this denominator into each term in the numerator. E to the 2x divided by e to the x. Remember, anytime you divide like bases, you subtract exponents. So that's going to be e to the 2x minus x, which is e to the x power, minus e to the 4x divided by e to the x. That's going to be e to the 4x minus x power, e to the 3x. So algebraically simplifying the inside, I get to this. Now we know that the integral of any exponential function is that exponential function divided by its derivative of its linear exponent. Pretty straightforward. The integral of e to the x is e to the x. The integral of e to the 3x is e to the 3x over 3. And of course, I keep the minus sign out in front of it. So I put it as minus 1/3 e to the 3x. And then we have plus our constant of integration. Next up, what if I have e to the x times the group e to the 2x plus 1 raised to the 4th power? Now, one thing that you might try here is you might think, well, what if I let u equal e to the 2x plus 1, and then du would have to be 2 times e to the 2x, which you could write the e to the x on the outside as a function of that. That's probably not the easiest way. The easiest way is just to go ahead and carry out the algebra here. We have this group raised to the 4th power. So I'm going to go ahead and expand that out. To expand it out, I'm reminding you over here of Pascal's triangle, where it says any binomial raised to the 1st power, well, raised to the 0 power, any number raised to the 0 power, including a binomial expression, is 1. If I raise something to the 1st power, I just have 1 of each. And then every other row, I start with a 1 and end with a 1. Every other number is the sum of the 2 above it. So when I expand out e to the 2x plus 1, my constant coefficients in front of each of the terms are going to be as follows. I'll have my, and notice I went ahead and did substitution here before I get to this part, so I'll talk about this first. I did go ahead and say u is equal to e to the x, so du is e to the x dx. That got rid of this part. But then you had that u squared plus 1 because e to the 2x is going to be equal to u squared here. So I had to raise to the 4th power u squared plus 1. When I do that, I can say, well, it's 1 times the 4th power of the first term. So that's going to be 1 times u to the 8th. Then it's going to be plus 4 times the 3rd power of the first term, which is going to be u to the 6th, and then times the 2nd, but that doesn't change anything, times 1, plus 6 times the 2nd power of the first term, u squared would be u to the 4th, and then it would be times 1 squared, doesn't change, plus 4 times the 1st power on the first term, that'd be u squared raised to the 1st, I get u squared, then you have times 1 to the 3rd power, and then your last term plus 1 times the first term to the 0 power times 1 to the 4th, you just get the 1. But again, if you need any help with that, you might just say, well, all he's using there to expand that out is Pascal's triangle. And if you just want to multiply that out by saying u squared plus 1 multiplied by itself 4 terms, you could, or 4 times, I should say, you could do that as well. But it would be more time consuming. Now, I just integrated each term using the power rule. I'll get u to the 9th over 9 plus 4u to the 7th over 7 plus 6u to the 5th over 5 plus 4u cubed over 3, and then plus u to the 1st. Of course, plus our constant of integration. And then we say, well, all right, that's in terms of u. We know u is equal to e to the x. So u to the 9th is e to the 9x. I have 1/9 e to the 9x plus 4/7 e to the 7x plus 6/5 e to the 5x plus 4/3 e to the 3x. And then u, of course, plus our e to the x plus our constant of integration. Okay, pretty good problem there. The next one, as soon as I'm looking at it, I have a polynomial in the numerator, polynomial in the denominator. I see the degree difference is 1. I'm expecting a natural log in the answer. There may be more than just the natural log, but I'm certainly expecting a natural log in the answer. Even if I wasn't looking at that, I know there's going to be a natural log. Denominator is x squared, numerator is x to the 1st. So I look at that denominator and I say, what if I let u equal that denominator? And I went ahead and wrote it in descending order. I know its derivative is going to be 6x minus 2, and that derivative is written with respect to x. Okay, so now if I simplify du here, I could say, well, I could factor a 2 out of that group and get 3x minus 1 dx. Well, fortunately, I see I have a factor of 3x minus 1 times dx in that numerator. The only thing I would need to do is get an additional factor of times 2. Well, I could easily multiply the inside by 2 and call all of that du if I remembered to divide by 2 on the outside. I did. That's what happened from here to here. I multiplied by 2 on the inside, and that 2 times 3x minus 1 times dx all became du, multiplied by 1/2 on the outside, and I was left with 1 over u du. Now, the integral of 1 over u is just the natural log of the absolute value of u. We have our 1/2 still multiplying it, plus our constant of integration. Now, we can say, well, we know that u is equal to that original denominator, so we just plug that in the place of u. Our final answer, 1/2 natural log of that quadratic plus the constant of integration. Just a few more problems here to look at with you. What if my numerator in a problem involves the natural log function squared, and I have an x in the denominator? This is going to be a pretty quick and easy problem. As soon as you see that you have an x in the denominator and you've got a natural log throughout the problem, you might want to go ahead and say instantly, let u equal the natural log of x. Why? Well, because the derivative of the natural log of x is 1 over x dx. That's going to get rid of that denominator. So I'll let u equal the natural log of x. Du is 1 over x dx. I understand the inside could have been written as the natural log of x quantity squared times 1 over x dx. Well, that times 1 over x dx part cancels out and becomes du. Well, then the rest is just u squared times du. Power rule now, that's going to be 1/3 u cubed plus c, which gives me the natural log of x. And please remember, you need to cube that entire natural log, not just the x on it. So I put parentheses around it, raise it to the third, divided by 3, plus your constant of integration. For 14 here, if I have an exponential function, does it matter if it has a fractional base? Not at all. Now, in this one, I went ahead and showed the substitution in the problem. You could have done it without the substitution. You could have just said, oh, it's an exponential function. What do I know about every exponential function? Every single exponential function, it's that, the integral is that exponential function divided by the derivative of its exponent and the natural log of its base, plus your constant of integration, done. Now, I showed that with substitution by letting u equal that exponent of 3x plus 2. But then the substitution would say, in order to allow that substitution, you have to see a factor of 3dx. I need to multiply the inside by 3 in order for that 3dx to become du. I could do that if and only if I divided by 3 on the outside. And then I have 1/2 to the u du inside the integral times 1/3. Then you still have to remember the integral of 1/2 to the u is going to be 1/2 to the u divided by the natural log of that base of 1/2. We still have our 1/3 out in the front, plus the constant of integration. Then you would need to distribute that 1/3 into the first term to get my exponential function divided by 3, natural log of 1/2, all of that plus your constant of integration. Now, again, I think these problems are easier if you'll just say the integral of any exponential function to a linear power is going to be that exponential function divided by the derivative of its exponent and the natural log of its base, plus your constant of integration. That will work every time the exponent inside your exponential function is a linear power. Number 15 here, and this is to be the last example for problems in this section. Then you should be ready to go tackle any of the homework problems. If I have some, and I love this problem, I have the integral of 5x plus 3 over x squared plus 1 with respect to x. So what I have to understand here is that, well, the degree of the numerator and denominator differs by 1. Okay, so there's going to be a natural log in your answer. Absolutely there is. However, it's problematic. Now, think about what I mean when I say it's problematic. You cannot easily obtain a factor of 2x in the numerator. So I'm saying, so split. Well, okay, as soon as I think about this, I'd say, well, could I do substitution? If I let u equal that denominator, du would be 2x dx. You cannot get a factor of 2x dx in that numerator. 5x plus 3 does not have a factor of 2x. So you say, okay, that's problematic. Well, no big deal. Anytime you have multiple terms in the numerator, you can split them up. And I can say, well, this is equal to 5x divided by that denominator plus 3 divided by that denominator in separate integrals. No problem there. You split up the integral. Now, is this going to make it easy? Yeah. You know that second one, that 3 can factor out front. You can say that's just going to be 3 times the integral of 1 over x squared plus 1, which by definition is your inverse tangent of x. So that one's going to be 3 inverse tangent of x. This first one's going to be where our natural log comes into play because the numerator is 1 degree less than the denominator. If I let u equal that denominator, then du is going to be 2x dx. And then I can say, well, I need to see a 2x dx up there. I see a 5. Well, I could factor that 5 out, and then I would have to force in a factor of 2x dx in order for that to become du. So if I have to multiply the inside by 2, then I divide the outside by 2. So notice that's where the 5 over 2 came from. And then the 2x dx all became du. So I have 1 over u du, which is going to be the natural log of the absolute value of u, which I know now is just x squared plus 1, and I don't even need the absolute value since x squared plus 1 is guaranteed to be positive. I'll have 5 over 2, natural log of x squared plus 1, plus the 3 inverse tangent of x we already talked about with that second integral, plus the constant integration. It's a gorgeous problem, guys. So let me know if you have any questions as you try the homework in this section. And this is, again, anytime you're dealing with substitution problems, this is a pretty important topic that you'll never be able to forget these techniques through future math classes.